You know that old mantra from the early Facebook days? The one that was plastered on every startup's wall for like a decade? Move fast and break things.
Oh, absolutely. It was the philosophy of the entire Web 2.0 era, right? Speed over perfection.
Right.
If there's a bug, you just ship it now, patch it later. It's all about velocity.
Exactly. And that philosophy works. Wonders if you're, say, Spotify, tweaking a playlist algorithm,
Yeah.
or Netflix A/B testing a thumbnail. The worst case scenario is what? A slightly annoyed user.
Yeah, a song buffers for 2 seconds. But imagine hearing that slogan from the pilot as you're boarding a plane.
That is a terrifying thought. Good morning, folks. Our philosophy today is to move fast and break things.
And that gut reaction you just had, that's really the core tension we're unpacking in today's deep dive. We're looking at the world of, well, safety-critical software systems.
This is the high-stakes table. We're
Yeah.
talking about systems where a software failure isn't just a bad user experience. It means, potential injury, massive financial loss.
Or even loss of life. Exactly.
Right.
And the big question is, how do you innovate in an industry that is, for very good reason, terrified of mistakes?
Because innovation usually means agile, iteration, speed, constant updates.
And safety-critical industries like aerospace have historically been, well, allergic to that. They like their processes slow, linear, and...
Very, very heavily documented.
But that's becoming a real problem. So we're diving into a fascinating case study today. It's a collaboration between the University of Porto and a company called Critical Software, or CSW.
And our mission here is to see if they can bridge this gap. We're exploring a concept called DocOps, automated documentation, to see if aerospace can finally move fast without, breaking the plane.
It's a huge shift in mindset. We're basing this whole discussion on a paper called Improving Documentation Agility in Safety-Critical Software Systems Development for Aerospace. It's a mouthful, but the ideas inside are pretty revolutionary.
So let's set the scene. We live in an agile world. The course material mentions a survey showing that something like 97% of organizations use Agile.
It's just the default now. You break work into sprints, you iterate, you release constantly. It's dynamic.
But when you look at aerospace, that number just drops off a cliff. They're mostly stuck with the waterfall model or the V model. I've seen diagrams of the V model, and it looks painful.
Yeah.
For anyone who isn't a software architect, could you break that down?
Sure. Just picture the letter V. You start at the top left and go down. That's your whole design phase, requirements, architecture, all of it.
Okay.
You hit the bottom point, that's where the actual coding happens.
Yeah.
Then you go up the right side of the V, and that's all your testing.
And the key rule, as I understand it, is you can't move to the next step until the previous one is totally signed off and documented.
Precisely. It's sequential, it feels safe because it's so rigid, but it is incredibly slow. And if you find a bug way over on the right side of the V during testing,
Oh, no.
you practically have to go all the way back to the start to fix the requirements and let the changes cascade down again. It's a nightmare.
Which is why the industry isn't doing it for fun. They're doing it because of certification.
Which brings us to the PLOS standard in the research, DO-178C.
The gold standard.
Sounds like a droid from Star Wars.
But much less fun and way more demanding. DO-178C is the guideline for airborne software certification. If you want code on a plane, it has to comply with this.
And it's not just about the code working, is it? It's not just, does the plane fly?
No, not at all. It's, can you prove that the code corresponds exactly to the requirements and that every single line has been tested and reviewed? You have to prove the absence of unintended behavior.
That's a high bar. Proving the absence of something is really, really hard.
And to do that, DO-178C requires a mountain of paperwork. I mean, specifications, design docs, code reviews, test cases, test results.
You end up with more pounds of paper than pounds of airplane. And the research says it doesn't walk alone. It has this whole entourage. There's DO-330 for tools, DO-331 for models. It's a regulatory labyrinth. And this is the Agile gap. Agile wants you to update software every 2 weeks. But DO-178C says if you change one line of code, you have to update the entire paper trail.
Ah, traceability.
Yeah.
That's the key word. So if I change a function in the autopilot, I have to trace it all the way back to the requirement, update the design doc, update the test.
All of it. Now imagine doing that manually in a 2-week sprint. You spend 3 days coding and 7 days writing Word documents.
Yeah, you're not doing Agile at that point. You're just doing fast coding followed by slow-motion bureaucracy.
And that's what the researchers found. Previous studies showed Agile techniques like pair programming. They actually work really well for writing safe code, but the documentation is the bottleneck. It just kills the velocity.
And the certification authorities, they see moving fast and they think cutting corners. They need to see the receipts.
So the researchers decided to stop fighting the paperwork and start automating it. This is where we get to DocOps.
I love this term. It's a riff on DevOps, obviously.
It is. DevOps automated the pipeline from writing code to deploying it. You push code, a robot runs the tests and puts it on the server.
So DocOps does the same thing, but for the documentation.
Exactly. Instead of a human writing a report, a machine generates it from the code itself. You commit your code, and the system commits the documentation right alongside it.
The source calls this a quasi-autonomous approach. Why quasi? That sounds like a cyborg.
It's a really important distinction. They're not saying, let ChatGPT write the safety manual. That would be a disaster.
I'm sorry, Dave, I can't open the pod bay doors because I hallucinated a safety protocol.
Precisely. We want to avoid that. It's quasi-autonomous because humans are still the architects. A human sets the logic, a human writes the requirements, and a human checks the logs. But the heavy lifting, the data gathering, the formatting, that's the machine's job.
So let's get into the nuts and bolts. What did they actually build?
Okay, first, their tech stack is interesting. Usually a company like CSW uses big enterprise tools, Jira, Confluence, Bitbucket.
The standard corporate suite. But they went rogue for this.
They did. They wanted something more generic and flexible, so they switched to GitHub and Python.
Python scripts and GitHub. That feels very hackery for aerospace. Almost punk rock compared to the usual stuff. Why that switch?
It proves the point. You don't need $1 million proprietary tool to solve this. You just need the right logic. Python is great for this, and GitHub has a fantastic API. So they built what they call a document management tool, or DMT.
And this DMT is a collection of tools. Let's start with the first one, the SCR generation tool. Break down that acronym.
SCRR. It's the Software Configuration Index Report.
That is maybe the driest name for a document I've ever heard. But for DO178C, this thing is the holy grail, isn't it?
It's the ingredients list. The SCIR identifies everything, every version of the software, every file location, every artifact ID, who wrote what.
So normally a human has to sit there and type all this out. File A is version 1.2 written by Bob.
Yes, for thousands of files. It's tedious, and more importantly, it's so easy to make a mistake. You type 1.2 instead of 1.3, and suddenly your certification is at risk because your documents don't match reality.
So how does the Python tool do it?
It uses the GitHub API. It literally just asks GitHub for the metadata.
So what are the steps?
First is data fetching. The script hits the API and just pulls down all the raw data commit hashes, file names, author tags.
The ground truth directly from the source code.
Right. Then there's the data parsing stage. It takes that data, usually in JSON format, and just organizes it.
And finally, the generation stage.
Where it spits out the actual document, but, and this is the really clever part, it also acts as a quality gate. It logs errors. So if a developer named a file wrong or an artifact is missing, the script flags it right away.
That's huge. It's like a spell checker for aerospace compliance. Instead of finding out 6 months later in an audit, the robot yells at you immediately.
Exactly. It does it in seconds and with higher accuracy than a human could manage over a week.
Okay, so that's the index. But knowing what files you have is one thing. Knowing you have all the right files is another. That brings us to the second tool, document traceability automation.
Right. This is for the certifiable data package. Before you deliver the software, you have to hand over this massive package of data. This tool verifies it.
It's the did I pack my passport checker.
A very good analogy, yes. It scans the repository for a list of mandatory files. The logic is actually quite simple. The script has a checklist for a specific certification level.
So if DO170C says you need a software test description, the script goes looking for, like std.docs.
Precisely. If that test report isn't there, it logs an error. Missing mandatory artifact. If everything is present, it confirms the package is complete.
The source mentions something interesting about versatility here. They designed it to handle not just DO178C for planes, but also EN50128.
Which is the standard for railways. Exactly. And that shows a key insight. The logic of safety-critical documentation is pretty universal. Whether it's a plane, a train, or, a nuclear reactor, regulators need to see the receipts.
So they built the bots. Did they actually work?
They were very rigorous in testing them. They used 3 criteria: correctness, maintainability, and performance.
Okay, correctness first. Did the robots make mistakes?
The short answer is no. as long as the inputs were right. They ran unit tests and compared the automated output to the manual templates. The scripts produced error-free documents every time.
That's the baseline, right? You can't trade speed for accuracy here.
Absolutely not. Then there's maintainability, and this is where that Python and GitHub choice really pays off. The code is modular. The part that talks to the GitHub API can be reused. If the standard gets an update in 10 years, they don't have to start from scratch. They just tweak the logic module.
And the big one, performance. Was it faster?
Drastically. They interviewed the professionals at CSW. It reduces the manual workload for sure. But the biggest finding was the reduction in mental workload.
That makes a lot of sense. As an engineer, I want to be thinking about aerodynamics and logic, not formatting the header on page 42.
Exactly. It lets the humans focus on the high-level safety analysis, the real thinking, not the clerical work. It moves the human up the value chain.
But we have to be honest about the limitations. We called it quasi-autonomous for a reason. What's the catch?
The catch is garbage in, garbage out. The tool is only as good as the data it gets. The researchers are very clear about this. It relies on developer discipline. You have to use the correct labels on pull requests, the right file extensions.
If a developer gets creative and labels a requirement as a test, the tool will get confused.
It'll flag an error, or worse, miscategorize it. So you still need humans to follow the process. But the biggest hurdle isn't technical, it's regulatory. The source states that these specific tools aren't yet qualified.
Back to the standards. This is DO330, right? Tool qualification.
Right. And this is a concept that can melt your brain a little. In aerospace, if you use a software tool to check your flight software, that tool also has to be certified.
It's the whole who watches the watchman problem.
Or tests the tester, exactly. You have to prove to the FAA that your Python script doesn't have bugs before you can use it to prove your flight software doesn't have bugs.
It's turtles all the way down.
It really is. So for this to be used on a real project, the scripts themselves would need their own qualification process. But this research proves the concept works. It's a huge proof of concept.
So zooming out, we've gone from a world where documentation is this manual anchor to a world where robots, simple Python scripts, handle the paperwork. What's next, according to the researchers?
They have big plans. They want to expand this beyond just indexing and traceability. They envision a pipeline with more gears.
I saw that diagram. Things like requirements generation and impact analysis.
Impact analysis is the real holy grail. Imagine changing one line of code and the tool automatically tells you, okay, this change affects requirement 42 and test case 12, you need to update those.
That would be true agility. That would take away the fear of touching legacy code.
And they're looking beyond aerospace, too. They specifically call out the automotive industry.
Self-driving cars.
Exactly. And all the driver assistance systems. They fall under ISO 26262.
Another catchy name.
We love our ISOs. But the principles are identical. If your car's software crashes, that's just as dangerous as a plane's. The auto industry is facing the exact same crisis. They need to move at the speed of Tesla, but with the safety of Volvo.
You know, this whole thing, it really changes the nature of the work. It's not just about speed. It's about shifting where the trust lies.
That's a really good point.
Which brings me to this thought I've been mulling over. If we get to a point where this stuff is fully automated, where a machine writes the proof that the machine is safe, does the role of the regulator change?
How do you mean?
Well, right now, a regulator reads a stack of documents. Did they test this? Yep. Signed off. Yep. But if a script generates that stack, shouldn't the regulators stop reading the documents and start auditing the script?
That is the billion-dollar question. Are you certifying the output, or are you certifying the factory that makes the output?
Exactly.
If the generator tool is proven to be flawless, if it's qualified to the highest level, then logically, anything it produces is compliant. It would fundamentally shift certification from a product review to a process review.
Which would be way more efficient. You audit the factory once, and then you trust the cars coming off the line.
But it requires a massive leap of faith in the tooling, and regulators are, paid to be paranoid. That's why DO330 exists. But yes, as these tools improve, the human role becomes less about checking boxes and more about designing the system that checks the boxes.
That's a fascinating shift. We always think of automation as robots taking our jobs. Yeah. But this feels more like robots taking the parts of our jobs that we hate and that we're bad at.
I mean, humans are terrible at consistently checking version numbers on 5,000 files. We get tired, we get bored. A Python script doesn't get bored.
And humans are great at understanding intent, context, and safety architecture, which a script is terrible at. It's a perfect partnership.
It really is.
So for everyone listening, whether you're coding flight controls or medical devices or just managing a project with way too much paperwork, think about your own workflow. What's the boring, repetitive part of your day that you tell yourself is necessary for quality control?
And ask yourself, is it actually ensuring safety or is it just bureaucracy? And could a script do it better?
There's probably a Python script waiting to be written that could save you 1,000 hours.
Or at least save you from the soul-crushing task of manual formatting.
And honestly, saving our souls is a worthy goal. That's all for this deep dive into agility in the skies. Thanks for flying with us.
Safe landings.